Welcome to the last video lecture for chapter 22. In this one, we will cover transformers and alternating current, pretty much the consequences of Faraday's law. The most important consequence is alternating current, as we'll see in a second, and as you can kind of gather from the idea of a changing magnetic field. This follows along through section 22.9 towards the end of the chapter. So follow along in your textbook. See you in a few seconds. I won't see you, but more. Let's continue. Let's go. All right. Alternating current is simply just current that switches back and forth in direction. Within our walls here in the United States, we have an alternating current that is about 60 hertz. So that means it switches direction 60 times in 1 second, back and forth. Now, the way to generate an alternating current, I think you've seen this before, heard about it before maybe. You have a turbine or something like that. Generally is what we have is have a turbine. And you have some generator which involves a loop of wire that is spinning in some magnetic field. So when you have the magnetic field or you have the loop of wire move, it creates a electric current within the wire. We've seen that from Faraday's law, induction. And from that wire, you get that current. Now, as the wire spins, since it's completing a full circle, the polarity of that current, or the EMF, the polarity of the EMF changes. It switches every 180 degrees. So that means that the current reverses direction. So as it moves back and forth, as the wire moves and loops and loops and loops, spins around and around and around, that's a little better to describe, that produces this current that alternates back and forth. It switches one direction. So first it's going, say, to the left, then to the right, then to the left, to the right, and within some wire. Now, within a complete circuit, it's alternating directions, clockwise, counterclockwise, clockwise, counterclockwise. And it happens so fast that we don't actually notice that. So we don't see that happening within a light. But so there's still that energy being able to be used by the device because it happens. 60 times in 1 second is pretty dang fast for the current to be moving, switching back and forth. There are different things where you can ramp it up so that you can always have like a continuous amount of energy instead of that little small, continuous amounts of current flowing through by doing current in different phases. So that's a little bit more into like electrical wiring and different stuff than what we'll talk about in here. But just understand that alternating current switches direction back and forth, and for the United States, it's about 60 times in a second. A transformer is a device that changes the voltage from a primary source to a secondary source. So it can either increase the voltage or decrease the voltage. Now, I sound really boring when I'm saying this, but they're actually really cool. And if you are watching this video, there was a fire in Boston, and this is in 2012, where there was a 150,000 volt transformer that caught on fire, and there was a big blackout. So it's going to be called the blackout of 2012 in Boston. But anyways, the way it works is there's some loops of wire around a solid core that's in a loop itself. And because it's an alternating current, those loops of wire create a magnetic field within that iron core, which is changing because it's alternating current, so the magnetic field is changing. And there's now a secondary coil or secondary loops of wire around this this iron core, where there is a voltage, or because of the changing magnetic field, there's an EMF induced on those coils. Now, the voltage difference between, or the ratio of the voltage between the primary coil and the secondary coil is related to the number of turns around the iron core on each the primary coil and the secondary coil. So you have the voltage of the secondary coil divided by the voltage of the primary coil is equal to the number of turns on the secondary coil divided by the number of turns on the primary coil. So just a ratio, it's just a ratio between the two, so you can have a step up or a step down transformer, which I'll talk about a little bit more in a second. Here I really just have what I was kind of saying before. I've written out in words, so instead of me speaking, you can actually read it right here if you're not getting the sound well, or if you're just looking for a little bit more of a complete explanation. The idea, you have two coils of wire around a solid iron core. That core, there's an alternating current current through one, and that creates a changing magnetic field that alternates back and forth within the iron core. And because of that, that induces an EMF in the second set of loops, which creates a voltage. And from that, you can either step up the transformer, step up the voltage, or step down the voltage. So I've been talking about this idea of a step-up transformer, step-down transformer. And what it really means is that in order to transmit the electricity produced for the power plant over a foot-long distance, because there is some loss, there's some resistance in the wire, and there's some power loss due to the wire, which depends on the current. So as you increase the voltage, the current's going to decrease. And so what happens is you get this, because the power plant can produce X amount of power, and so if you ramp up the voltage, you will get step up the voltage. I keep saying ramp up, which is not right, but just my tendencies to do it. You must get down and step up the transformer. This is Arnold going to help you out with this. The step-up transformer, anyways, the step-up transformer increases the voltage from the power source, so that way it can be transmitted over a longer distance with less power loss due to resistive heating, and other things within that. And then at the other end by your house, you need to have a step-down transformer, which translates that voltage to a lower voltage. It's a bigger step-down transformer. You'll see these outside of cities, towns, and then you have another step-down transformer right outside your house. This is those boxes on the telephone poles, etc., and they're right there, and they step it down to something that your house can use in a little bit simpler way. So, transformers, pretty straightforward, one equation, just the idea that they change the voltage. All right, question for tonight's video. A booklight has a 1.4 watt, 4.8 volt bulb that is powered by a transformer, which is connected to a 120 volt electrical outlet. Very common that you'll have something like this in your house at home. The secondary coil of the transformer has 20 turns of wire. First question, how many turns does the primary coil have? This would be the coil coming from the electric outlet. And second question, what is the current in the primary coil? So you can go through and you can calculate this. One thing we can say here is we can assume that this is a ideal transfer and there's no loss of electrical energy. So the power in the primary coil is going to equal the power in the secondary coil. All right, thank you. Put this again, answer this online, and have a great evening. All right, welcome to a little supplement to this video on transformers. So here I actually have a transformer right here, and I'm going to hold it up to the screen, and you can see, and hopefully that I'm getting that right on there, but you can see on the bottom part there was input 120 volts, output 12 volts DC, so the input was in AC and it converts it into DC, and I'll talk about that in a second. And the output current is 800 milliamps, so you can hold that up there. You can see that. So if you were to actually calculate it, the output power would be 9.6 watts. And I'm looking at my calculator right now because I did it out before. And if you were to go through and you use the power formula, the idea that it's a ideal transformer, the amount of power is the same output as the input. That means it's taking 0.08 amps of current from the wall. Now what I'm doing here is I'm going to open this up. And we see here from where it plugs into the wall, there's wires connected to one coil. And this is a little different than what we saw in the video. But there's one coil here, which therefore is going to create a magnetic field in this iron core, and it's very heavy. You can look at it in class. And then there's another coil right here that's connected to this little switchboard here. And this switchboard has what we call diodes on it. And some of these diodes are connected in parallel, and some of them are in series. There's a certain way that you can go through and you can connect these diodes, so that way it takes this alternating current that's going back and forth in different directions, and when it reverses, a certain diode will charge up and it will allow the current to keep moving through. So that it'll actually get, and that's where we have this capacitor right here. So there's a constant flow of energy. So you have a capacitor and a couple of diodes, and you have an output right here going to whatever this was plugged into that I then took apart. I have no idea. It's just got a kind of generic plug in the end. But it will provide a constant direct current to that source. And so this is how, like, mini little transformer, kind of the idea of like that light bulb problem right there that you saw. And you have a lot of these little adapters, the AC to DC adapter, 120 volts to 12 volt DC, something like that that we have. So boom, there it is, little mini transformer with an adapter in it. So diodes use the adapter. They limit the direction that alternating current can go. Thank you very much. Make sure to put your question answers in online, and I'll see you tomorrow in class.